Okay, so the last time we talked a little bit about, by way of introduction to quantum mechanics, a little bit about an experiment called the Two Slit Experiment, in which light and electrons were thrown at these two slits in a screen, and out of both of those things, despite us usually thinking about electrons as particles, these little BBs that go whirling around an atomic nucleus and carry a little bit of negative charge, despite us thinking about those as particles rather than waves, we got an interference pattern, this pattern of constructive and destructive interference that gave us a light and dark banding pattern on a screen, a solid screen that was set behind the two slits. This is weird stuff, and the idea, though, that all the bits and pieces of the world around us have wave and particle properties, essentially depend on how we look at them and in what context, this idea is known as wave-particle duality. It's not that an electron is all a particle or all a wave, it's that it is kind of both all the time, and depending on what it is that we're trying to do with it, it can exhibit one or both of those sets of properties. Okay? So let's talk a little bit more about that experiment. Here's some data from an actual two-slit experiment where what they did is they took a fairly fancy set of equipment to fire electrons at the slits one at a time. Just one. So it's not like you sent in this barrage of electrons and they somehow formed some sort of wave pattern and then created that interference pattern, those bright, dark, bright, dark, bright, dark bands. It's that if you prepare a whole bunch of nominally identical electrons and you fire them away one at a time, well, after you've got, let me grab my laser pointer here, after you've got, maybe 100 electrons, the detection screen behind the two slits looks something like this. Pretty random, right? Doesn't seem to be much of a pattern. But you keep going, and you start to see the bright and dark banding, okay? And as you go farther, okay, it starts being more and more apparent. And as detectors got better, this is a relatively old experiment, you can do the same kind of thing these days, and you can get that bright and dark banding just like you do with a light wave, okay, which we know to be an electromagnetic wave. Remember, the screen and particle experiment looks kind of like this. So you've got your two slits, you send in a whole bunch of particles, whether you're doing it one at a time or whether you're doing a bunch at once, and they exhibit wave-like properties. In other words, they go through these apertures, they clearly have some sort of wavelength, so they have those concentric rings coming out, and they interfere with one another, and so what you get is little clusters of detection. So these clusters of detection there, and these sort of peaks of bright, so lots of detections, followed by dark in between, right? So something like, get a different color here, something like this, right? So bright, dark, bright, dark, bright, dark. Okay? This is kind of weird, because if they were particles, there would be no reason for them to do this, okay? You don't get constructive and destructive interference unless you have waves, and yet nominally we think about electrons as these particles that carry charge and whirl around nuclei and flow through wires to give us electricity and all of this kind of thing, and yet here they are acting like a wave, like light. And this is one of the kind of bonkers things that quantum mechanics gives us. And it's not just electrons that act this way. All sort of quantum entities have this wave-particle duality to them. So if you're talking about electrons or protons or whole atoms or even collections of atoms, then you can do experiments that show this kind of property where sometimes they act like particles and sometimes they act like wave and sometimes they act like both of them at the same time. And that kind of thing is fundamental to what quantum mechanics is, which is a little mind-bending, but as we will see as we move through this unit, has some fundamental effects on the world around us and also on some of the technologies that we use every day and that we're dependent on. Now, the next thing I'd like to talk about in the context of this experiment is what happens if we are like, well, you know, these things must be going, we're convinced these are particles. So we're going to set up some detectors and we're going to figure out as each electron comes flying in which aperture, which slit it's going through. Is it going through this one, in which case I'm going to detect it with this detector, or is it going through this one, I'm going to detect it with this detector, and every time I see one going through this aperture, then this detector is going to give me a little click, and I'm going to know that it went through that one. And if I know that it went through that one, then I should be able to see particle here, right? There's a click from the particle, and then I should be able to see the particle, you know, show up over here on the screen, okay? So I'm going to track this thing down. The wave properties, this kind of experiment is kind of suggesting that these things are somehow going through both openings and interfering with themselves, essentially, and creating this light-dark pattern that we see over here on the left. Okay, that's just bonkers. We don't believe it. We're going to detect things, and we're going to know for sure which one of those apertures it goes through. The thing is, if you do this, right, if you modify the previous experiment, where we didn't have any detectors figuring out which aperture they went through, we just knew they had to go through the apertures because obviously they showed up on the screen afterwards. If we put the detectors in there, what happens is it goes back to sort of this particle behavior, right? We just get clicks, or we get, you know, detections on our screen like we would over here, but we get detections on our screen just in line with the slits, with the apertures in this screen. Okay, so suddenly there's no interference, and they're acting like particles, and our detectors will click, clickety, clickety, clickety away. If we count 20 particles coming up here and landing there, we will get 20 clicks on a detector, and same thing down here. Okay, so everything would sort of work as we might expect it to if we really wanted to know which one of those things went through. So what gives? Because we haven't changed the electrons, we haven't changed the two slits, we haven't really changed the experiment. The only thing we're doing is we're peeking, right? Before we see the results over here on this screen, we're essentially trying to get a little preview, right? We're going to figure this out. We don't believe this whole wave thing, and indeed, when we sort of take this peek, suddenly everything looks like electrons are acting like particles. Well, that doesn't actually disprove anything, right? It just shows us that, again, an electron can act like a wave and like a particle. So, but why is that thing, that detection that's done in that version of the experiment, why is that the thing that so dramatically changes the result that we get on our screen over here? Okay. So this comes to another fundamental thing. When you're talking about a quantum object, okay, all quantum objects, and by quantum objects I'm usually referring to things that are sort of roughly on the atomic size scale and smaller, though there are larger scale things that exhibit quantum properties, as we'll talk about a little bit as we move through this section. But quantum mechanics does best in describing the properties of these very small particles. Okay? In any case, when you're looking at one of those quantum entities, one of those quantum objects, well, all these physical properties, position, velocity, and it's summed up by what's called a wave function of the particle. And that wave function can only tell us about the probability distribution for that particle's, position, say. Okay, that's what we've got graphed down here. So we have position on the x-axis, and we have probability on the y-axis. And not all particles, if this is a sort of free electron shooting through the air, this probability distribution isn't the one that describes all of the particles in all situations. This can change quite a bit depending on whether the electron is bound to an atom, or whether it's free and wandering off, or whether it has higher energy or lower energy. Anyway, so wave functions can vary, but this is just sort of a prototypical thing. And if we think about the property of position, right, we'd like to know where that electron is, sort of like we did when we set up these detectors in this experiment. Well, quantum mechanics tells us that if we were to measure the position of this electron, right, we use a detector, we figure out where this thing is, well, then the most probable position is right here. Right, whatever position that is, 2 meters from whatever point, okay? Doesn't matter. But the peak here, right, is probability. So its peak probability is right there at that position. But of course, that's only the peak probability. It could just as well, you measure it, show up over here, albeit at a much lower probability, and it could just as well show up over here, or technically over here, with very low probability, but the point being that you have one electron of a certain type, or rather one electron in a certain situation, and you measure its position, and the wave function of that electron is going to tell you the range of positions you might expect and the probabilities of each one of those positions. When you measure, though, if you were to do this measurement and you were to say, okay, we're going to measure this thing and I'm going to figure it out, well, now, of course, the probability of it being in that position that you just measured it to be is right there, right? If we found it at the most probable position, boom, right? Probability of 1, okay, to be at that position at that time because we just detected it, we measured it, okay? So quantum mechanics doesn't defy reality, right? If we use a very sophisticated detector and we figure out that the electron, we make a measurement, we make sure that the electron is right there at this time, then we've found it, okay? But prior to that time, prior to that measurement, we only know about the probability of it being within a certain range of positions, right? And if you were to take another identical electron, same situation, just another electron in the same situation so that it has the same wave function and all that kind of thing, and you were to measure it again with this very sophisticated detector, the chances of you getting it to be at that exact position right there is, well, relatively small. It might, okay, but it's going to show up somewhere within the probability distribution of the wave function that describes that electron's properties, okay? Said one way, a measurement of a quantum object collapses, quote unquote, its wave function and reduces, throws away all of the other probabilities and collapses it to a certainty, okay, like we've shown over here on the right, okay? Now, it's worth also exploring the idea that if we go back to sort of miniaturized versions of those experiments that we talked about last time, so this one with the detectors before the slits and this one without, so we get interference, and so lots of bright dark interference bands here, and then just 2 little spots in line with the slits if we actually use detectors to figure out which slit the electrons are each going through. Both of these situations involve measurements. It's just here on the left, right, where we have no detectors prior to the things going through the slit, well then the position of these electrons has not been determined, right? It's still, the wave function has not collapsed. It has some probability of going through the left, some probability of going through the right, and in a sense, it goes through both. And in that instance, it exhibits its wave properties, it interferes, it creates this constructive and destructive interference that gives us all of these bright and dark bands on the screen over here. The measurement here that occurs here is on the screen, because of course, to get those bright and dark bands, we have to detect the position of the electron, where it collides with the screen here, okay, or doesn't collide in the case of the destructive interference parts, okay? So there is a measurement here, and we do locate the electron, but only after it has interfered and exhibited its wave-like properties. Whereas here, Well, we've collapsed its wave function. We've made it go from this broad distribution of probability in position, possibly going through one aperture or both or whatever, okay, or rather having a probability of going through both apertures, to definitely going through one or the other, or maybe neither, okay. And in that case, well, then the electron definitely goes through that and definitely goes through here and essentially is reduced to its particle-like properties by this pre-slit measurement. All right? That's a weird thing. If you really think about it, why should that make any difference at all? Okay? And that's why in the early 20th century, well, technically there's some of this, a little bit of this stuff was going on in the late 19th century, but early 20th century, why very famous physicist Einstein was very doubtful of some of the predictions of the sort of infancy of quantum mechanical theory back then. And the idea that the universe is not mechanistic, that there's a probability distribution, for instance, to the position or the energy or the velocity or the momentum of electrons and protons and atoms and all of these kind of things, rather than it being determined by stark physical laws, well, that didn't sit well with a lot of physicists at the time, and it took a long time and many, many experiments demonstrating the accuracy of quantum theory that gives you these probability distributions for the particles for the larger physics community to come around. So, next time we will be talking a little bit about that, just to touch on the science history side of things. And we'll be talking about some of the early experiments that demonstrated both the wave and particle-like properties of a couple of different particles, and the quantized nature of things like energy levels around atoms. So we have that to look forward to, and hopefully I'll be able to post that very soon. See you then.